All right, team, let's jump straight into this architecture explainer. We're tearing down the finalized Sex Display architecture inside SexOS. Today is all about doing a deep read of our architecture brief and postmortem docs. We need to track exactly how we're locking down our visual invariants. We're going to break down the precise mechanics of how we get from raw user intent all the way to hardware scanout, and how we are permanently nuking the legacy flaws you'd normally see in traditional display servers like Wayland.
Here is our roadmap for today. We'll hit core system invariants, MPK isolation and routing, the proven DSRE pipeline, critical fixes and ABI hardening, silicon resilience and SFDP, and finally, proven reality versus next work. Let's get right to it. Section 1. Core system invariants. We absolutely have to establish the non-negotiable rules of our single address space operating system, or SASOS.
This sets our absolute baseline. The system is officially categorized as broken if a scheduler tick occurs in Sexdisplay without altering the frame buffer. No output is an illegal state. I mean, that perfectly illustrates our visual liveness guarantee. We are running with zero POSIX or Linux assumptions here. No reliance on standard libraries, no lib, no threads, no cross-protection domain pointers. All communication is strictly PDX only with bounded weights. Because of this, a silent black screen or a hidden deadlock, that's just an invalid state. Every single tick has to result in a UI frame, an idle frame, or a red error frame. No exceptions.
And that brings us to the DSRE, the Display State Reduction Engine. This completely replaces your traditional compositor. So unlike a legacy event loop compositor that haggles with clients, Sexdisplay is just a pure math function. The DSRE acts as the sole frame buffer writer, period. It has absolute DRM master, single writer authority. It just wakes up at the VBlank interrupt, samples the global scene graph, and compiles it straight into a DRM atomic commit.
All right, moving into Section 2, MPK isolation and routing. How exactly do we safely move data around if the whole system shares one single 64-bit physical memory map? Take a look at this hardware protection key mapping. Notice how we're routing capabilities without copying a single byte of memory. This is our strict Intel Memory Protection Key, or MPK isolation, in action. The kernel sits in PKey 0, acting as the routing authority. Then, our compositor, Sexdisplay, completely owns PKey 1 along with the physical frame buffer. Over in PKey 3, we have our UI shell, Silk Shell. So when Silk Shell needs to talk to Sexdisplay, it does it entirely through the PDX capability edge at slot_display, which is mapped to slot 5. Just look at the massive difference here. In legacy Wayland on Linux, you were paying for heavy context switches, completely isolated processes, and expensive CR3 page table swaps just to move a simple buffer. But in our SexOS SASOS model, the entire system lives in one global 64-bit physical memory map. We leverage Intel MPK for zero-copy handovers, which means the kernel literally just flips a hardware PKRU bit to grant memory access. This gives us a completely lock-free, weight-free core. It is insanely fast. Let's transition to Section 3, the proven DSRE pipeline. We're looking at the physical execution layer now. This right here is the crucial takeaway, our exact proven pipeline to the pixels. First, Silk Shell calculates the UI intents, what we call UIR, in ring 3. It fires that IPC call right through the PDX capability edge at slot_display. The kernel validates it, flips the hardware lock, and boom. Sexdisplay, functioning as our DSRA, wakes up, reads the memory 0 copy, and shoves it directly into a DRM atomic commit and the gem-dump buffers. It lands flawlessly at the EDP scanout. So we have this incredibly fast, mathematically provable graphics pipeline built out of raw CPU primitives. But it begs a really critical question. How on earth do we prevent the system from suffering silent state desynchronizations during such a rapid handover? You all know that high-frequency IPC environments expose those nasty hidden hardware hazards that can just tank a system. And that brings us to Section 4, critical fixes and ABI hardening. This is the post-mortem crucible where we dive into the fatal flaws we recently uncovered and patched up. We were facing a massive silent desync hazard with syscall 28. In the old design, the system used the RAX register equaling 0 as a null sentinel to say, hey, the queue is empty. But think about it. What if a hardware interrupt fires exactly between the ring buffer dequeue operation and the syscrit queue restore? That RAX register could get completely clobbered.
The kernel would return a no message status even when valid data was sitting right there. That caused Sexdisplay to spin endlessly in a ghost state, giving us a totally silent black screen. We liquidated this syscall28 register clobber hazard for good by ripping out that fragile REX equals 0 logic. The output contract is now strictly registers only. We enforce a tightly typed PDX message struct where type ID hex 00 is strictly permanently reserved for PDX empty. Problem solved.
We also ran into and patched the headless compositor bug. The kernel was doing its job correctly tagging the physical firmware pages with PKI1 for Sexdisplay, but our software routing table was totally empty. Because of that, Silk Shell was physically barred from communicating with the compositor, which triggered a null pointer jump. To fix this, we explicitly granted the slot_display capability edge right in init.rs. This successfully bridged our hardware isolation to the software routing, meaning Silk Shell can now issue its op_window_create commands with 0 issues. Moving on to Section 5, Silicon Resilience and SFDP, we need to have a serious chat about surviving unpredictable GPU hardware. If you're building a high-performance machine, you have to accept that the GPU is occasionally going to hang. The only perfect design assumes hardware failure. Because of that, we completely threw out persistent frame buffer mutation and replaced it with a fence-driven plane graph compositor, or FDPC. We also wired up the Silicon Resurrection system. If the Intel iGPU locks up, this system kicks in using a last good frame latch. It guarantees that the scanout continues flawlessly using the last valid frame, completely decoupling our scanout lattice from the failure-prone compute lattice. To enforce this, we built the Single Frame Depth Deterministic Present Pipeline, or SFDP. This establishes one absolutely strict invariant. There is a maximum of 1 GPU frame in flight per CRTC. If the previous frame's outfence hasn't signaled yet, the system literally just drops the next frame instead of queuing it up. It acts as a brutal, strict admission gate that totally eradicates render queue buildup, latency spikes, and any of that nasty compositor-induced jitter. Finally, Section 6, Proven Reality versus Next Work. Let's clearly define what is actually shipping right now versus our immediate next targets on the roadmap. Looking at our proven column, we have completely locked down the PDX syscall ABI. The atomic KMS mode sets and gem-dumb buffer handoffs are fully verified, and the DSCRE and SFDP core fully functional. Now, looking ahead to our immediate next work, we are going straight after the NVIDIA Prime Optimus DMO buff handoffs, and crucially, we're targeting total Wayland elimination via a lattice shim, along with finalizing the Universal UI IR compilation.
Team, I really want you to think about the implications of this pipeline. By locking down these invariants, we aren't just building another standard Wayland compositor. We are completely collapsing the event loop. We are transforming the GPU from a basic I/O device into a pure deterministic state evaluator. We are building a real-time visual operating substrate. Keep these invariants hard-coded in your minds as we push toward the next phase. That wraps up this architecture explainer.